And let me start sharing my screen. So let's go to that. All right, everybody could see where it says multiplication rule for independent events. Oh, dang. All right, so let's see. All right, so today we're going to be extending the multiplication rule. So when we're doing the multiplication rule, where we're doing it for two random selection. So right now we're going to be doing it for multiple random selections. So we're going to be doing it for more than two selection, because the independent rule, you can apply it for if you do two selection, you can also do three selection, you can do four selection, you can do infinite many selection. So let's go ahead and let's see this first problem. So for the first problem, it says the probability that a randomly selected 40-year-old male will be alive to be 41-year-old is 99.855%. So we'll say probability, oh, that's pretty thick, that a 40-year-old will be alive is 0.99855. So that's what that first sentence give us. It's telling us a random 40-year-old male, the probability that that random 40-year-old male will survive and become 41-year-old is pretty much 99.855%. So let's go ahead and let's look at A. So if you look at A, it says, what is the probability that two randomly selected 40-year-old male will live to be 41-year-old? So the most important thing right now that they're giving us, they're telling us that we're doing two randomly selection. So that means we're going to be doing multiple selections. So that's why we're going to do the multiplication rule. So if you look at this one, we want to find the probability that the first person or the first 40-year-old male is alive to be 41. But we also want the second 41-year-old to be alive when they turn 41. So we want both of them to be alive. So in order to find that probability, we're going to find the probability that one of them is alive. And we're going to multiply it by the probability that the second one is alive. Any question in regard to that formula so far? All right. So let me get class calc for that way we could start doing the math. All right. So if you look over here, I already said the probability that a 40-year-old male is alive to be 41 is 0.99855. So that's what we're going to put right here. We're going to put 0.99855. And we also want the second person to be alive. So you're going to get that value and multiply it again. 0.99855. All right, so let me switch it over to class calc. So what we're going to go ahead and do, we're going to go ahead and do that math. So let's share class calc. So we're going to say 0.99855, and we're going to multiply that by 0.99855. And if you multiply it out, if you look at the result that we get 0.9971. All right. And that's it for that first part. Any question in regard to how we did that first part? All right. So let's do part B. All right. So if you look at B, it says, what is the probability that 5 randomly selected 40-year-old male will be alive to be 41-year-old? So for this one, if you look at it, we're now saying instead of 2 randomly selected people, now we have 5 randomly selected people. Yeah, so we have 5 randomly selected people. So for this one, you want the first person to be alive, you want the second randomly selected person to be alive, the third person to be alive, the fourth person to be alive, and lastly, we want the fifth person to be alive. So we want all 5 of them to go from 40-year-old all the way to 41-year-old. Yeah, pretty much that's what we're gonna do, Imani. We're gonna just get the probability and we're gonna multiply it 5 times. So for this one, we're gonna get probability of A, and we're gonna multiply that by probability of A again. We're gonna multiply that by probability of A again, and pretty much we're gonna do that how Imani said, and we're gonna multiply it 5 times. So we're gonna do 0.99855. But instead of putting 0.99855 times 0.99855 5 times, we're going to use the exponent because the exponent is the other way to do multiplication. So since I'm going to multiply this 5 times, you're just going to put this to the 5th power. All right, so let's go ahead and let's do that. So I'm going to switch over to class calc. All right. So what we're gonna go ahead and do, we're gonna say 0.99855. And if you look at class calc, if you look right here, it has this button, a to the n power, where you go ahead and use it. Okay, if you look right now it's saying put an exponent. So now we're gonna put the exponent. The exponent in this case is just gonna be 5. And if you look, that should be our answer for part B. So we're gonna say point, oops, I'm blocking the answer. 9928, and that'll be your final answer for part B. So pretty much all we're doing, we're just expanding it from saying if we're doing 2 random selection, we could expand it if we're doing 3 random selection or 4 random selection or 5 random selection, which the last one was a 5 random selection. All right, but that's it for that problem. Any question for that last problem? Okay, so up and we're gonna go ahead and do, you're go ahead and we're gonna watch this video. So let's see, hopefully I could get this video to pop up.
Closest thing to a real life Sherlock Holmes.
Stop share. All right, give me a minute. Apparently, it doesn't want to share on my iPad, so let me find the video on YouTube.
I think you're fantastic.
Closest thing to a real.
Stop share. And we'll say share YouTube. All right. Can everybody see the YouTube video right now that said American Got Talent 2017 Colin Cloud? All right, sweet. All right. So all you have to do is just watch this video and
Life mind reading, people show their true selves and their deepest, darkest secrets. Today I'm going to tell the world what the judges are really thinking. I'm here to show the millions of people watching something hopefully they have never seen before.
Hi. So what's your name and how old are you?
My name is Colin Cloud and I have just turned 30.
And what are you going to be doing for us today?
Today I'm going to show the world the closest thing to a real-life Sherlock Holmes.
You can look at a person and know their age, what they do for a career.
It's actually easier if I give you a quick example of what I do before we get to the main event.
Okay.
The lady at the front, would you hold up your two hands just like this? Yep, just hold. Okay, would I be correct? If I'm wrong, be honest. Are you a teacher? Yes, that's your job. The guy beside this lady, not moving, but the body language. Are you a police officer? Yes.
No!
I'd love to teach you how some of this works. Would that be okay?
Yes.
Yes. Before we go any further, Tyra, would you mind joining me, please? Your turn. Hi, Tyra. I won't embarrass you, okay? You're very safe. Tyra, grab a seat on this this stool. You're going to hold this prediction that may prove very important very soon. My background genuinely is in criminal profiling, specifically detecting when people are lying. So with this in mind, I want to teach you how this works with a very simple game that I learned as a child, starting with Howie. Howie, I'm going to give you a coin. I will also give you an antibacterial wipe, should you request it. All I want you to do is place the coin behind your back, please. Try to give nothing away, but hold your hand straight out in front of you like this. Give nothing away. Just say yes both times. Does that make sense? Yes. That was perfect, Harry. Right. Is the coin in this hand? Yes. Is the coin in this hand? Yes. Now, when he said yes for real, when he meant it, his eyebrows raised slightly. Really? Your nose is also pointing slightly here, so I believe it's in this hand. Turn it over. Let me see. Yes. Yes. There it is. Okay, now, I want to try this with the three of you as well. What I'd love you to do now, place the coin behind your back. Everyone on this side of the room, think of a simple color. In the middle, think of any animal. And over here, think of any name. Hold your hand straight out, Mel, facing me. Shout those colors nice and loud in 3, 2, 1, go! White or blue. Perfect. So look at me, straight face. If the coin's in this hand, think white. If it's in this hand, think blue. Look at me, just think. Is it white? Just think. Or is it blue? I believe you're thinking white. The coin is here. Turn it over, let me see. Yes.
I was harder than Howard.
Oh, yeah, no, you were much harder. We'll do this quicker, okay? So again, Heidi, if you'd be so kind, hide it and your hand straight out in front of you. Those animals, any animal, go! Cat or cheetah. Cat or cheetah. It must be in one of your hands. Hold them straight out with absolute aggression, Heidi. I love it. Right. If the coin's in this hand, think cheetah. If it's in this hand, think cat. So look at me. Really send the animal, okay? I am petrified. You are thinking, cat, the coin is here. Turn it over, open it up. Yes, 2 out of 2, ladies and gentlemen. Good. Simon, be so kind. Behind your back, sir. Either hand. Those names, any name, shout them. Hold on. Charlie or was yours? Oscar. Okay, Charlie or Oscar? Hands out in front. Straight face. If the coin is in this hand, think Charlie. If it's in this hand, think Oscar. And I get distracted sometimes when I do this. The blonde girl behind you is looking very nervous, hoping I don't reveal one of her embarrassing memories. Don't move. Look at me. Are you thinking about a memory when you were a kid? But there's a name involved with this that you were thinking, and we've never met before. Be honest, we don't know each other. The last name, is it Miller? Yes, okay, right. So, Simon, if it's in this hand, it was Oscar, this hand, Charlie. You're thinking Oscar, the coin's here. Let me see, turn it over, open it up, let me see. Yes, Oscar, yes! But here's the thing. Before I walked onto this stage tonight, I had some ideas about the type of audience you were going to be, and I wrote them down on a scroll. Now, you guys could have shouted anything, or judges could have heard anything and picked anything, but tonight, you wanted the color white, you went with cat, and you picked Oscar. You will see, this scroll actually says that I, @Colin_Cloud, want you to open the lid and tell everyone what's inside.
I'm scared.
Would you please stand up? Open the lid. I don't want to touch. Open. Yep, I'll take this. Open the lid. Open the lid. Look inside. Open it.
Oh my gosh.
And inside of here is a white hat. But wait, cameraman, would you come over here? The name tag also says Oscar. Thank you, Tyra. Thank you.
Can I play with the cat while we judge?
All right, so let's go over that. So let me share back the screen. All right, so everybody should be seeing my screen again. So it should say H, M, H, K, and S. So let's kind of go over this. So if you want, you can either shout out the answer or you can type it in the chat. So for this trick, if you kind of notice, there was like two parts to the trick. One of the part where choosing the name from the audience, and then also being able to predict which coin, well, which hand the coin was in. But if you kind of listen to the name that the audience was shouting out, can you really hear what the audience was saying, or was it kind of just like all jumbo?
Jumbo.
Yeah, cause you really couldn't hear. So I'm pretty sure, like once he went out, he already knew he was gonna pick the color Y. He already knew that the animal he was gonna choose was a cat, and lastly, that the name that he was gonna choose was Oscar. So that part of the trick wasn't really that impressive, because I'm pretty sure he already had it pre-planned where he was gonna say like, okay, I heard the Y, I heard cat, and I heard Oscar. So the part of the trick that we're kind of going to go over is him being able to guess correctly which hand the coin was in. So for this one, you kind of first have to see, like, are they independent events? So they are independent event, because if he would have gotten Howie correct, it doesn't affect the probability of him getting Mel B correct, or Hayden Klum correct, or Simon Cowell, because each one of them are independent from each other. So once he got one correct, it doesn't make him more easier or less easier. Is essentially the probability will be the same. So let's go over the probability. So for Howie, what would be the probability that he would have gotten Howie correct? Well, how many hands does Howie have? Cool. So he has 2 hands. And in how many hands did he have the coin? Like, did he have the coin in both hands? Yeah, cool, Brian. So he only has it in one hand. So the probability that he would have gotten Howie is 1 out of 2. All right, what would be the probability for Mel B? So what would be the probability that he would have guessed correct which hand Mel B had the coin? All right, same thing. 1/2. And it should be the same thing for Heidi and Klum. It should be 1/2. And lastly, for Simon Cowell, it should also be 1/2. So we're saying they're independent from each other. And the reason why they're independent from each other, because if you look at it, this probability doesn't affect the probability of this one, which doesn't affect the probability of this one, which doesn't affect the probability of that one. So that's why we say they're independent events. All right, so far, any question I got 1/2 times 1/2 times 1/2 times 1/2. All right. So all we're gonna do now, we're gonna multiply this. So if I do 1 times 1 times 1, well, you get 1. If I do 2 times 2 times 2 times 2, you get 16, which will be 0.0625. Or if you want, you could say 6.25%. Right. And that's it for part A. Any question for part A? All right. So let's look at the percentage. So the percentage is telling us like how likely or how unlikely he is of getting this trick correct. So if he is doing this randomly and just guessing for all 4 judges, the probability that he get all 4 judges correct is 6.25. So that means if he does this trick 100 times, so if he does this trick 100 times, that means 6 of the 100 times he get it correct. So does that mean it's very likely that he get it correct just by guessing, or does that make it like pretty unlikely that he get him correct just by guessing? Well, it should be that it's pretty unlikely that he get it correct just by guessing. Because kind of think about it, you don't want to really take a trick that only works 6 of the 100 times. You kind of want it to work a little bit more. So up next, we're going to do part B. So for part B, it says, does it seem that he could have guessed right all 4 times by random luck? Or can he read the judge's micro expression to tell what hand the coin was in? So which one's more likely, that he guessed them just by random luck, or he could read their micro expression? So in the chat, you have to either type in random luck or micro expression. All right, so that's one person. Yeah, so for this one, we'll say it is more likely he is a magician. So we could say it was magic. Oh, sorry about that. All right, so yeah, so we're gonna say it's more likely that he could read their micro expression because by randomly guessing, he only has a 6.25% chance of getting it correct. So if we only have two options of going like, is he doing this by random luck or is he doing this by actually reading their expression and that's how he's getting it correct? It's more likely he's reading their micro expression versus just randomly guessing which hand the coin will be in. All right, that's it for B. Any question in regard to B? All right. So what I want you to do now, I want you to practice on these next two parts. So I want you to take a minute. So I'm going to be opening up a poll for them. So try doing this problem right now. So let me open up a poll for you. So once you get your answer, either you choose A, B, or C. All right, so a little bit, then half of the class has answered. So I'm gonna give you one more minute for that way you could answer the question. And then we'll move on to part B. All right, so let me share the poll with you. So let me end And now let me share the result. All right, so if you look at it, which one had the most vote for? So A, B, C, or D, which one had the most vote? Yeah, so if you look at it, B had the most vote. And in this case scenario, B was actually the correct answer because the way you should have gotten this for this one, we have 3 randomly selected babies, and we want them all to have green eyes. So we want the first baby to have green eyes, we want the second baby to have green eyes, and we want the third baby to have green eyes. So we say 0.06 multiplied by 0.06 multiplied by 0.06, and that should have gotten you B. All right. And that's it in regard to that question. All right. Any question in regard to A? Okay, so now we're gonna do B. So same thing, work out B. Once you're done working out B, all I want you to do to A, B, C, or D, I'll put in the answers right now. So. All right, so try doing B. So once you're done working out B, either select A or B or C or D. Okay, here. Sorry about that. Let's say stop share. All right, so there you go. So those are the options that you have to choose from. All right, so I'll give you like 30 more seconds and then we'll move on from this problem. All right, so let me share the result with you. I'll share the result. All right, so if we're looking at the result, which one had, well, which one did more people choose? So did they choose A, B, C, D? So which one did they choose? Yeah, so if you look at it, most people chose A. So A was 55%. Well, 55% of you chose A, and actually A was the correct answer. So let me go over how you should have gotten an A. So if you look at this one, they tell you that the first baby has green eye. So you say 0.06. Then they tell you the second baby doesn't have green eye, so you say 0.94. Then they tell you the third baby does have green eye, so you say 0.06. So if you actually go ahead and multiply that out, you should have gotten A. And just remember the way that you get 0.94, because if I know the probability that they have green eyes is 0.06, to get the probability that it's not green, you say 1 minus the probability is green, which gets you the 0.94. So in case you were wondering where does the 0.94 come from, that's where the 0.94 come from. You get the probability that you have green eye, and since they're mutually exclusive, you either have green eyes or you don't have green eye. That's why you can say 1 minus 0.06. Right, but that's it for that problem. Any question in regard to that last problem? All right, so that's it for the multiplication rule. So up next, what we're gonna go ahead and do, we're gonna start working on a conditional probability. So for a conditional probability, this is the notation that we're gonna use. So the way that we read this, well, P is probability. And then if you look right here is A. So probably that the event A occurred. This vertical line right here, whenever you see a vertical line, that means given that. So whenever we see anything after the vertical line, this means whatever's right here has already happened. So what I mean that has already happened, that means we already know that event has already happened. So kind of think about it, if I tell you probably you have an umbrella, given that it's raining. So the given information is that we already know it's raining. So the way we would write that, we'll say probability, you bring an umbrella, given that it's raining. So whatever information we put here, that's the information we already know. So just know that vertical line means given that, and whatever comes after that vertical line is telling us that that has already happened. Everybody kind of good on how to read that notation? All right. So let's scroll on down. So up we're going to do part A. So if you look at part A, it says the table below show patient status and the hospital the patient went to. So for part A, it says use a conditional distribution to identify association among hospital and survival status. So we want to see, does it depend on which hospital you go to, whether you'll survive or not survive? So what we're going to go ahead and do, we're going to go ahead and find these probabilities. So we're going to find the probability somebody survived given that they went to hospital A. We're also going to find the probability somebody survived given that they went to hospital B. All right, so those are the two probabilities we're going to be working on right now. So let's go ahead and find the first one. So if you look at the first one, the given is that they went to hospital A. So since they went to hospital A, that means we're only going to look at people who went to hospital A. Because that's the given information. That's what we already know has happened. We already know they went to hospital A. So how many total people went to hospital A? Yeah, so we have a total of 2,100 people went to hospital A. So right here we'll say 2,100 people went to hospital A. Of the 2,100 people who went to hospital A, how many of them actually survived? So thanks, Kimberly. So you get 2037. So we're going to do 2037 divided by 2,100. So it's like 2037 divided by 2,100. If you divide the two, you should get 0.97 or 97%. All right, and that's it for that first conditional probability. Any question for that first one? All right, so let's do the second one. So the second one said probability survived given they went to hospital B. So in this case, the given, we'll do this in neon green, is that they went to hospital B. So now we only want to focus on people who went to hospital B. So how many total people do we have that went to hospital B? Yeah, so we have 800. And then if you look at it, we have 784 people who survived. So we're going to do 784 divided by 800. And you get 0.98 or 98%. Any question in regard to how we got that percentage of 97% or 98%? All right. So up next, we're going to go ahead and we're going to look to see if there's an association among hospital and survival status. So if there is an association, that means we're going to see a great difference between these two probabilities. So is there a major difference between 97% and 98%? No. So since there's not that much of a difference, we're going to say no association. So if there's a huge gap between the two of them, we're gonna say there is an association because that means it does matter what the given information is. But in this case scenario, if you look at it, if I change the hospital, the percentage only changed by a little bit, so that way we put no association. And that's actually it for this one. B is pretty much the same thing. So what we're gonna go ahead and do, we're gonna go ahead and do the next problem, and then that'll be it for today's lecture. So up next, we're gonna go ahead and do the ultrasound reliability. So we want to see if the ultrasound is more reliable for one gender. So if you get an ultrasound of a baby, we want to see like which one is it more accurate for? Is it more accurate for female or is it more accurate for male? So let's go ahead and do part A. So if you look at part A, it says find the probability a newborn baby is female. So before we actually do that, let's kind of go over the two-way table. So if you look right here, it says ultrasound predictive female. So that means it was a prediction based off of the ultrasound. So it's saying like the ultrasound predicted the baby should be female. So it's not telling us the baby was actually female. It is saying the ultrasound predicted the baby should be female. If you look at this one is telling us the ultrasound predicted that the baby will be male. So you're saying the ultrasound predicted female, the ultrasound predicted male. For this one, if you look at it, it says actual gender is female. So that means once the baby was born, they were actually able to see that the baby was actually female. Same thing for this one. This one, once the baby was born, they were actually able to see that the baby was a male because once they had the baby, you could see that it was a male or a female. All right. Any question in regard to the two-way table? All right. So for part A, it says find the probability a newborn baby is female. So we just want to find the probability is female. So how many total baby actually turned out to be female? Well, if you look right here, this means actual gender is female. So if I use this row, you're able to get 480. So we get 480 of the baby were female. And then for this one, since there is no limitation or there's no given information, you divide by 1,000 and you get 48%. But that's it for A. So for this one, since we just want to know how many baby were actually female, you just want to get how many total baby were female from each category, and you get a total of 480. All right. Any question in regard to 480 divided by 1,000? All right, so let's do B. So for B, it's saying find the probability a newborn baby is male. So in this case, we just want to see how many of them turn out to be male. So how many total baby do I have that actual gender is male? Yeah, so you have 520. Same thing divided by 1,000. And you get 52%. Right. And that's it for B. Any question in regard to B? All right, so let's do C. So for C, if you look at it, it says use the given information to estimate the probability that a newborn baby is female, given the ultrasound predicted the baby will be female. So right here, the key word is given, or given that. So that means everything after that, this is the known information. So that's information that I know. So that means when we're finding the probability, we're saying, because we want to find the probability the actual gender is female. So we'll say actual gender is female, given the ultrasound predicted female. All right. So for this one, we want to find the probability the baby will actually female, given that the ultrasound predicted the baby will be female. So let's try getting this one. Here, so let me erase all of this mess. So if you look at what's the given is that the ultrasound predicted a female. So that means we only want to focus on this column over here. Okay, we only want to focus on babies that were predicted to be female. So how many total babies were predicted to be female? Yeah, cool. Thank you, Kimberly. So you should get 562. So of the 562, how many of them actually turned out to be female? Yeah. So if you look right here, of these 562, 432 actually were female. So you do 432. So I'm going to do 432 divided by 562. So I'll say 432 divided by 562. Oops. And you roughly get 76.9%. So that's just telling me if the baby were predicted to be female, 76 or pretty much 77% of the time, the baby is actually female. And that's it for that last problem. Any question for that last problem? Oh, for that part. All right, so let's do part D. So for part D, it says use the given information to estimate the probability a newborn baby is male, given that the ultrasound predicted the baby will be male. So for this one, once again, we have the given that. And then after the given that, it's saying the ultrasound predicted the baby will be male. So for this one, we want the probability the actual gender is male. Given that the ultrasound, predicted So that's what we want to find for the second one, because it says given that, and then it says given that the baby was predicted to be male. So what we want to go ahead and do, we're going to go ahead and we're now going to be using this portion of the data set. Because now the information telling us we already know the ultrasound predicted the baby was a male. So how many babies were predicted to be male? Yeah, so 438. So you got 438. So now, if you look at of the 438, we want to see of them how many of them actually turn out to be male. So of the 438 baby that were predicted to be male, how many of them turn out to be a male? Well, for that one, you want to be careful because you just told me how many total female there are. If you look at it, we want male. So the male should be the 390. So you want to say 390 divided by 438. So you get 390 divided by 438. And you get 89.04%. Any question in regard to how we got 89.04%? All right, so let's look at part E. So for part E, it says, based on your answers to part C and D, do you think ultrasound is equally reliable for predicting gender for boys and for girls? Explain. So if you look at the percentage of the baby that were predicted to be female that actually turned out to be female, it was roughly 77%. If you look at the ultrasound prediction for male, it was 89%. So are they equally reliable, or is it more, or would it be a little bit more reliable for male or for female? So which one is more reliable? Cool, yeah. So put more reliable for predicting. Yeah, so we'll put more reliable for predicting male than female because if you look at the percentage, there's a pretty good gap between 77% and 89%. So for this one, you could also say there's an association because depending on which gender it is more likely or less likely that it will actually be correct. All right, but that's it for E. Any question in regard to E?